Welcome to physics class. Good morning, everyone. My name is Muhammad Gyashuddin. My dear students, today we are going to discuss about numerical problem based on particle trapped in one-dimensional box. Numerical based on particle trapped in one-dimensional box, and this is our lecture number 20 and part number 2. Okay, so our first numerical problem is the electron is confined to move between two rigid walls separated by 10 to the power minus 9 meter. Okay, find the first three allowed energy state states of the electrons and the corresponding energies okay. Mass of electron equal 9.1 into 10 to the power minus 31 kg, and Planck constant 6.62 into 10 to the power minus 34 joule second. Okay, so this is our first numerical problem. The statement of this problem: the electron is confined to move between two rigid walls separated by 10 to the power minus 9 meter. This is clear that 10 to the minus 9 meter this is the width of the box. Okay, and find the first three allowed energy state of the three electrons and the corresponding to energies. Mass of electron is 9.1 into 10 to the minus 31 kg, and H equals 6.62 into 10 to the power minus 34 joule second. Okay, so now we are going to solve this question. Solution. The given information of this question: L equal width of the potential wall, that means L equal 10 to the power minus 9 meter, and also given Planck constant H equal 6.62 into 10 to the power minus 34 joule second, and mass of electron, this is equal to 9.1 into 10 to the power minus 31 kg. Okay, and find the first three allowed energy state. That means for first energy state, say we can write n equal 1, 2 and 3, and our corresponding energy E1 equal what, and E2 equal what, and E3 equal what. Okay, so we know that En equal n square h square divided by 8m l square. Okay, and we can write E equal n square h square divided by 8m l square, and we know that the value of h equal, that means n square into 6.62 into 10 to the power minus 34, and divided by 8 m, this is the mass of electron, so we can write 9.1 into 10 to the power minus 31 kg, sorry, 31 into L. This L is equal to 10 to the minus 9 meter, okay, 10 to the minus 9. After solving this part, we can write 6.02 into 10 to the power minus 2 into n square, okay, and this value we can convert in electron volt. So as we know that 1 electron volt equal 1 EB equal 1.6 into 10 inverse 19 joule. So we can write 6.02 into 10 to the power minus 2 divided by 1.6 into 10 to the power minus 19 electron volt, and this is equal to 0.38 n square. So this is our energy. Now we are going to find out corresponding energy for n1, n equal 1, 2, 3. Okay. So again, for n equal 1, then E1 equal 0.38 into the value of n equal 1 square. So finally we can write 0.38 electron volt. Okay. And again n equal 2, then we can write E2 equal 0.38 into 2 square, and this is equal to 1.52 electron volt. 1.52 electron volt. 1.52 electron volt. And again n equal 3, then we can write E3 equal 0.38 into 3 square, and this is equal to 0.42 electron volt. So this is our corresponding energy E1, E2, E3 for corresponding n1, n equal 1, 2, 3. Okay. So for your better understanding, I am going to repeat this once again. The statement of this question: the electrons is confined to move between two rigid walls separated by the 10 to the power minus 9 meter. That means 1 nanometer. Okay. And find the first 3 allowed energy state of the electron and the corresponding energies. Mass of electron is 9.1 into 10 to the minus 31 kg, and H equal Planck constant 6.62 into 10 to the minus 34 joule second. From this question, we can collect the information. Length, this is potential width between potential wall. Okay. H is Planck constant 6.62 into 10 to the minus 34 joule second. This value is already given in our question, and mass is also given in our question. M equal 9.1 into 10 to the minus 31 kg, and n equal orbit number 1, 2, 3. Okay, or quantum number 1, 2, 3, and its corresponding energy E1, E2, E1 equal what, E2 equal what, and E3 equal what. Okay, we know that En equal n square h square 8 ml square 8 ml square. Okay. Now E equal n square, the value of H equal 6.62 into 10 to the minus 34, and 8 into m, mass of electron 9.1 into 10 to the minus 31 kg, and L equal 10 to the power minus 9. Okay. After solving this part, we can write 6.02 into 10 to the minus 2 into n square. Okay. And this value we can convert in electron volt, because we know that 1 electron volt equal 1.6 into 10 inverse 19 joule. So when this value divide in this value, then we can convert electron volt. So we can write E equal 0.38 n square electron volt. Okay, electron volt. Now we are going to find out corresponding energy n equal 1, 2, 3. So E1 equal 0.38 n square. That means the value of n equal first value 1. So 1 square. After solving this part, we get 0.38 electron volt. Similarly, n equal 2, then E2 equal this, and similarly n equal 3, then E3 equal 0.42 electron volt. Thank you. Okay, our next numerical problem is this. The statement of this problem: calculate the energy required for an electron to jump from ground state to second excited state in a potential well of width L. Okay, so the given information of this question, solution. Given mass of electron, this is clear that particle is electron. So mass of electron M equal 9.1 into 10 to the power minus 31 kg. Okay, and H, this is Planck constant, H equal 6.62 into 10 to the power minus 34 joule second. And suppose ground state N1 equal 1 and N2 equal 2. First excited state, this is N2 equal 1, and for ground state N1 equal 1, we can write. Okay. And excited state. Okay, calculate the energy required for an electron to jump from ground state to second excited state in a potential well. First of all, we are going to find out energy associated with first energy state. Okay, so we can write E equal. We know that this is the energy expression. We have En equal n square h square divided by 8m L square. 8m L square. Okay. This is the energy level expression. This is the energy level expression for the particle. This formula is known as energy level expression for particle trapped in one-dimensional box. Okay. So this is our main formula. For ground state n equal 1, we can write. So suppose E1 equal n square h square divided by n1 square divided by 8m L square. So suppose this is the equation number 1. Again for excited state, first excited state for n equal n2 equal 2, then we can write E2 equal n2 h square divided by 8m L square. So suppose this is our equation number 2. Now required energy this is equal to E2 minus E1. Okay, the value of E2 equal n2 square h square divided by 8m L square minus E1, the value of E1 equal n1 square h square divided by 8m L. Okay, ml square. Now we can take common part, h square divided by 8m L square divided by n2 square minus n1 square. Okay, the value of n2 equal 2 square. Okay, so we can write h equal divided by 8m L square divided by 2 square minus 1 square, and after solving this part we can write 2 square, that means this is 4 minus 1, this is equal to 3, so we can write 3h divided by 8m L square. 3h divided by 3 for first excited state. So we can change just a value of n2, so this is 3 and 3 square, and 3 square means this is equal to 9, and 9 minus 1 equal 8. We can write 8. Okay, 8 and 8 cancel to each other. Finally we can write E equal energy required E equal h divided by 8m L square. 8 divided by h divided by 8m L square. Okay, now since the value of L is unknown, so we can put just the value of h and m. So finally we can write h equal 6.62 into 10 to the power minus 34 and divided by m equal 9.1 into 10 to the power minus 13 into L square. Okay, after solving this part we get something, this is divided by 1 by L square. So this is our required energy. Okay, for your better understanding I am going to repeat this once again. The statement of this question: calculate the energy required for an electron to jump from a ground state to second excited state in a potential well Woods L. Okay, the given information of this question we can collect. This is the given information. Okay, mass of electron equal 9.1 into 10 to the minus 31 kg, and h, as we know that the value of h equals 6.62 into 10 to the minus 34 joule second. Suppose for ground state n1 equal 1 and n2 equal 3. Okay, n1 equal 1 and n2 equal 3. We have E and n square h square divided by 8 ml square, and this is the energy level expression for particle trapped in one-dimensional box. This formula is called energy expression particle trapped in one-dimensional box. Okay, so first of all we are going to find out E1 equal n1 h square divided by 8 ml square. So suppose this is our first equation, and for n2 equal 2, for excited state second excited state n2 equal 3. Okay, for this is E2 equal n2 divided by h square. Okay, so this is our second equation. Okay, required energy E equal E2 minus E1, the value of E2 equal this and the value of E1 equal this. Okay, and now we can take some common term h square 8 ml square, Okay, so h square divided by 8 ml square divided by into n2 minus n1. Okay, the value of n2 equal 3 square and n1 equal 1. So 1 square. After solving this part, we can write h divided by 8 ml square. And in this case, the value of L is unknown quantity. Okay, the magnitude of L is unknown. So just we can put the value of H 6.62 into 10 to the minus 34, and the mass value of the electron 9.1 into 10 to the minus 31 kg. After solving this simple part, this part, we get something into divided by 1 by L square. So this is our final answer. Thank you. Okay, our next numerical problem is this. The statement of this numerical problem: an electron is constrained to move in one-dimensional potential box of length 0.1 nanometer. Okay, find the first three energy eigenvalues of the corresponding de Broglie wavelength and calculate the energies difference between the ground state and first excited state. So first of all, the solution of this problem: 0.1 nanometer. This is clear that this is length of the, that means width of the potential wall. An electron is constrained to a move in a one-dimensional potential box of length 0.1 nanometer. So length of the potential one-dimensional box is 0.1 nanometer. So given L equal 0.1 nanometer. As we know that nanometer is not SI unit of the length, so it should be converted in SI system. So we can write 0.1 nanometer. This is equal to 0.1 into 10 to the power minus 9 meter, and this is equal to 1 into 10 to the power minus 10 meter. Okay, and also Planck constant H equal 6.62 into 10 to the power minus 34 joule second. Okay, and particle is electron, so the mass of the particle 9.1 into 10 to the power minus 31 kg. Okay, and find the first three energy eigenvalues of the corresponding to de Broglie wavelength. It means that E1 equal what? E1 equal what? E2 equal what? And E3 equal what? Okay, and this corresponding wavelength lambda 1 equal what? Lambda 2 equal what? And lambda 3 equal what? Okay, and for first three energy state, we can write n equal 1, 2, and 3. Okay, so we know that En equal n square h square 8m L square. Okay, suppose E equal n square, the value of h equal 6.62 into 10 to the power minus 34, and 8 into m, this is equal to mass of electron, so 9.1 into 10 to the power minus 31 into L, the value of L equal 1 into 10 to the minus 1 into 10 to the power minus 10 meter. Okay, after solving this part, we can write n square equal n square into 6.03 into 10 to the power 6.03 into 10 to the minus 18 joule. Okay, 18 joule. Now we are going to find out E1, E2, E3 corresponding value n equal 1, 2, 3. Okay, so first of all, E1 equal, we can write E1 equal n square, that means E equal n square into 6.03 into 10 to the power minus 18 because the value of h square by 8 ml square, this is equal to this. Okay, so the value of n equal, for n equal 1, that means for n equal 1, then E1 equal 1 square into 0.63 into 10 to the power minus 18 joule, and this is equal to 6.03 into 10 to the minus 18 joule. So this is our value of capital E1. Okay, again for n equal 2, that means when n equal 2, then we can write E2 equal the value of n equal 2 square into 6.03 into 10 to the power minus 18, and this is equal to 24.12 into 10 to the power minus 18 joule. This is second energy state. Okay, And again, n for n equal 3, for n equal 3, for n equal 3, for n equal 3, that means when n equal 3, then we can write E3 equal 3 square into the value equal 6.03. Yes, 6.03 into 10 to the minus 18, and this is equal to, we can write 54.27 into 10 to the minus 18 joule. Okay. So the given information of this question, length of potential box equal 0.1 nanometer. We know that nanometer is not SI unit of the length, so it should convert it in SI system. So we can write 0.1 into 10 to the minus 9 meter, and this is equal to, we can write 1 into 10 to the minus 10 meter. Okay. Second, H, this is Planck constant, and the value of Planck constant equals 6.62 into 10 to the minus 34 joule second, and M, mass of particle 9.1 into 10 to the minus 31 kg, and E1, E2, E3, the energy state corresponding to n equal 1, 2, 3. Okay. And lambda 1, lambda 2, lambda 3, its corresponding wavelength lambda 1, lambda 2, and lambda 3. So first of all, we are going to find out E1, E2, and E3. Already we have calculated. Okay. Now we are going to find out lambda 1 and lambda 2 and lambda 3. Now, again, de Broglie wavelength, we are familiar with this formula, lambda equal h by mb. This is equal to lambda equal h by under root of 2me. So we can write lambda equal h by under root of 2me. Okay. So this formula we can write lambda 1 equal h by under root of 2me1. Okay. Now the value of h equals 6.62 into 10 to the power minus 34, and the value of m, that means 2 into m, this is equal to mass of the electron. So we can write 9.1 into 10 to the power minus 31 into the value of E1. The value of E1 equals 6.03 into 10 to the minus 18. Okay. So we can put 6.03 into 10 to the minus 18. After solving this part, we get 2 into 10 to the minus 10 meter. 2 into 10 to the power minus 10 meter. Okay. Similarly, we can write lambda 2 equal h by under root of 2m e2. Okay. 2m e2. Now the value of h equals 6.62 into 10 to the power minus 34, and the value of 2 into mass of electron 9.1 into 10 to the power minus 31, and the value of E2 equal to 24.12. Yes, 24.12 into 10 to the minus 18. After solving this part, we get this is equal to 1 into 10 to the power minus 10 meter. Yes, 1 into 10 to the minus 10 meter. Again, lambda 3 equal, similarly, we can write h equal under root of 2m E3. Okay, E3, and the value of h equals 6.62 into 10 to the power minus 34, and 2 into the value of mass value of the electron 9.1 into 10 to the power minus 31 into the value of E1. Okay, so the value of E1 equal the value of E1 equal, yes, exactly 6.03. Yes, 6.03 into 10 to the minus 18. After solving this part, we get this is equal to 0.667 into 10 to the power minus 10 meter. So finally we can write the de Broglie wavelength corresponding energy state E1, E2, E3. We can write lambda 1 equal this is equal to 2 into 10 to the power minus 10 meter. Okay, and lambda 2 equal 0.667 into 10 to the power minus 10 meter. Okay, and lambda 3 equal this is equal to lambda 3. Okay, sorry, this is lambda 3. Okay, so lambda 3 equal 0.667 into 10 to the power minus 10 meters. Lambda 1 equal 2 into 10 to the power minus 10 meter. Okay, and lambda 2 equal 1 into, sorry, lambda 1 equal 1 into 10 to the minus 10 meter, 1 into 10 to the minus 10 meter, and lambda 3 equal 0.6 is 7 into 10 to the minus 10 meter. Okay. Now, according to the statement of this question, one important corner is here. Calculate the energy difference between ground state and first excited state. Okay. Now we are going to find out energy difference between ground state and first excited state. As we know that for ground state n equal 1, okay, and first excited state n equal 2. Okay. Now the energy difference, second part of this question, okay, the energy difference between ground state and excited state, first excited state. Yes, first excited state, we can write, say suppose the energy difference we can denote by capital E. So we can write this is E2 minus E1, okay, E2 minus E1. Okay. The value of E2 equal, we have already calculated the value of the E1 and E2, okay. So the value of E2 equal 24.12 into 10 to the power minus 18 minus divided by E1. The value of E1 equals 6.03 into 10 to the minus 18. After solving this part, we get the result is okay. In this case, we can take just 10 to the minus 8 and 10 to the minus 8 we can take commonly. Okay, so 10 to the power minus 18 into 24.12 minus 6.03, and finally we can write 18.09 into 10 to the power minus 18 joule. So this is our final answer. For your better understanding, okay, for your better understanding, I am going to repeat this once again. The statement of this question: an electron is constrained to move in a one-dimensional potential box of length 0.1 nanometer. Okay, find the first three energy eigenvalues of the corresponding de Broglie wavelength. Calculate the energy difference between the ground state and first excited state. So according to question, we can collect the data. Say suppose H is Planck constant, the value of H equals 6.62 into 10 to the minus 34 joule second. According to question, the given information of this question, particle is electron. So this is clear that mass of electron is 9.1 into 10 to the minus 31 kg. Okay, and potential, the length of the one-dimensional box is 0.1 and 0.1 nanometer, and so this is L equals 0.1 nanometer, and 0.1 nanometer is equal to 10 to the minus 10 meter. Okay. First of all, we are going to find out En equal n square h square divided by 8 ml square. Okay, so this is the energy expression. The expression of energy associated with particle trapped in one-dimensional box. So we can write, or we can use En equal n square h square divided by 8 ml square. Okay, so first of all, we are going to find out energy E1, E2, E3 corresponding the value n equal 1, 2, 3, and second, we are going to find out lambda 1, lambda 2, lambda 3. This is the de Broglie wavelength corresponding to orbit number n1, n2, n1, n equal 1, 2, 3. Okay, thank you. Okay, this is our last numerical problem. The statement of this problem: an electron is confined to move between two rigid walls separated by 1 nanometer. Find the de Broglie wavelength, the first two allowed energy state. Okay, so 1 nanometer separated between two rigid walls. So this is clear that this is the value of L, that means width of the wall. Okay, so solution: the given information of this question, L equal 1 nanometer, and we know that nanometer is not SI unit of the length, so it should be converted in a SI system, and we know that 1 nanometer, that means this is equal to 10 to the minus 9 meter. So finally we can write 10 to the power minus 9 meter. Okay, and Planck constant H equals 6.62 into 10 to the power minus 34 joule second, and particle is electron. This is clear that particle is electron. So mass of particle is, as you know that mass of particle is what, 9.1 into 10 to the power minus 31 kg. Okay, we have need to find the de Broglie wavelength, the first two allowed energy state. Okay, so that means lambda 1 equal what and lambda 2 equal what. Okay, now we know that En equal n square divided by h square divided by 8m n square. Okay, En equal n square h square divided by 8m n square. Okay, again we know that we know that lambda equal h by under root of 2me. This is the expression of de Broglie wavelength in terms of energy. Okay, this is the expression of de Broglie wavelength in terms of energy. So lambda equal h by under root of 2me. Okay, the value of E equal this. Okay, so the value of E equal this value we can put in this equation. So we can write lambda equal h by under root of 2m into E. The value of E equal n square h square divided by 8m l square. Okay, n square h square divided by 8m l square, and this is equal to h divided by under root of this m and this m cancel to each other. 2 4s are 8. Okay, so we can write n square h square divided by 4l square. Okay, yes, 4l square, and the root of n square h square 4l square we can write lambda equal h divided by h square. It means that the root of h square is n. The root of n square, it means that n. Okay, and root of h square is single h, and divided by root of 4 is 2, and root of l square is n. Okay, now lambda equal h divided by nh divided by 2l. Okay, and this part we can arrange in this way: h into twice l divided by nh. Okay, so h and h also cancel to each other, and finally we can write 2l divided by n. Okay, so this is the value of lambda. Now we are going to find out lambda 1 and lambda 2 for particularly n equal 1 and n equal 2. Okay, now lambda 1 equal 2l divided by n. Okay, the value of L is, this is clear, the value of L equal 1 nanometer, and 1 nanometer is equal to 10 to the minus 9 meter. So we can write 2 into 10 to the power minus 9, and the value of n equal 1. Okay, so finally we can write 2 into 10 to the power minus 9 meter. Okay, this is the value of lambda 1. Again, similar way, we can say that lambda 2 equal 2l divided by n. Okay, so for second time we can put 2 into l. The value of l equal this is equal to 10 to the power 9. Okay, and the value of n equal 2. The value of n equal 2 because we know that n equal 1 and n equal 2 for 2 allowed state. Okay, so 2 and 2 are cancelled to each other. So finally we can write 10 to the power minus 9 meter. So this is our final result. The value of lambda 1 equal 2l divided by n, and lambda 2 equal 10 to the power minus 9 meter. For your better understanding, I am going to repeat once again this problem. The statement of this problem: an electron is confined to move between two rigid walls separated by the 1 nanometer, and find the de Broglie wavelength, the first two allowed energy state. Okay, first of all, we are going to collect the whole information from this question. So length, this is clear that the separation between two rigid walls, this is the value of L. So L equal 1 nanometer. And nanometer is not a SI unit of the length, so it should be converted in SI system. So we can write 1 into 10 to the minus 9 meter, and this is equal to 10 to the power 9 meter. Okay, and H equal Planck constant, and the value of Planck constant is 6.62 into 10 to the minus 34 joule second. And the mass particle is electron. This is clear that, so we can write the mass value of the electron is 9.1 into 10 to the minus 31 kg, and lambda 1 equal what and lambda 2 equal what, corresponding to n equal 1 and n equal 2. Okay, quantum number n equal 1 and quantum number n equal 2. This corresponding value lambda 1 equal what and lambda 2 equal what. Okay,
we know that the energy expression particle trapped in one dimensional box, we can write En equal n square h square divided by 8 mh square. Okay. Okay. So the value of En, the value of En, we can write as we know that lambda equal h by under root of 2me. This is the mathematical expression of de Broglie wavelength expression, the expression of de Broglie wavelength in terms of energy. So we can the value of En, this value we can put in this equation. Then we can write, after solving this part, finally we get lambda equal 2L by n. Okay. Now we are going to find out lambda 1 and lambda 2. Since lambda equal 2L by 1, 2L by n, for quantum number n equal 1, then we can write lambda 1 equal 2L divided by n. And the value of L equal this. Okay. So 2 into 10 to the minus 10, 10 to the minus 9, and n equal 1. So after solving this part, we get 2 into 10 to the minus 9 meter. Similar way, we can say that lambda 2 equal 2L divided by n, and 2 into 10 to the minus 9. Okay. Because the value of L equal 10 to the minus 9. And in this case, n equal 2. So 2 and 2 cancel to each other. Finally, we get 10 to the minus 9 meter. So this is our final result. Wavelength, de Broglie wavelength lambda 1 and lambda 2 corresponding to n equal 1 and n equal 2. Okay. Thank you.